So welcome to this session. This session, we are going to give some functions and prove that those functions are harmonic. That's to mean that the functions satisfies Laplace equation. So Laplace So just remember that any function that satisfies the Laplace equation is called harmonic. And then Laplace equation comes in different forms, in different dimensions. So if we have a function f of x, y, which depends on two functions, so this is in 2D, then the Laplace equation is partial squared f partial x squared plus partial squared f partial y squared equals to 0. So this is the case of 2D. If we have a function f of x, y, z, this is in 3D, then the Laplace equation takes the form partial squared f partial x squared plus partial squared f partial y squared plus partial squared f partial z squared equals to 0. And you can similarly express a Laplace equation for other higher dimensions. So let's start with the examples. Our first example, show that the function given by the function given by f of x, y equals to e raised power ax sine of ay satisfies the Laplace equation. So trivially, this is the case of Laplace equation in 2 dimensions because the function is only depending on x and y. So to prove this, so proof so we show that partial squared f partial x squared plus partial squared f partial y squared equals to 0. So this is what we call the Laplace equation in 2 dimensions because we have an x and y. So let's get partial f partial x. In this equation here, this is the only function that depends on x. So by chain rule, to differentiate this part, we get a, and then so we'll have a e raised power ax, and then sine of ay. And then this implies that partial squared f partial x squared will be, now differentiate this one again with respect to x. So differentiating this power, we get a, then multiply by this, we get a squared e raised power ax, and then sine of ay. So that is with x. Now let's go to y. So partial f partial y will be, this is the only function that has y, so also use chain rule. So differentiate this part with respect to y, we get a, then pre-multiply by this. And you know, when you differentiate a sine function, you get a cos function. So we'll have a e raised power ax cos of ay, which implies that partial squared f partial y squared. Now you differentiate this function again with respect to y. So using chain rule, this part will give us a, and when you differentiate a cos function, you get negative sign. So we'll have a minus sign. So that a that we got here, we multiply by this, gives us a squared, and then we have e raised power ax, and then sine of ay. So then now we have to add the two equations. Partial square, so this implies that partial squared f partial y squared plus partial squared f partial squared y, partial, this is x, equals to a squared e raised power ax sine of ay, and then plus this other one is minus a squared e raised power ax sine of ay. I hope clearly you can see that this is zero, because this and these are the same terms with opposite signs. So that is the proof that that function satisfies Laplace equation. Problem 2, show that the function phi given by phi equals to phi of x, y, z equals to 1 over the square root of x squared plus y squared plus z squared satisfies the Laplace equation. Now, these are cases whereby we prove Laplace equation in 3 dimensions. So, solution. We show that partial squared f partial x squared plus partial squared f, not f, this the function is phi, so we use phi in terms instead of f. So partial squared phi, and then this is phi partial y squared plus partial squared phi partial z squared equals to 0. So partial phi partial x will be, now remember this function can be written as just to make our life easier, note that 1 over square root of x squared phi equals to this is the same thing as writing x squared plus y squared plus z squared raised power minus a half, just using laws of indices. Remember, square root means raised power a half. So when I put in the numerator, then this the same function. So when it's in this form, it will be now easier to work out the derivatives. Partial phi partial x. Now I use chain rule, whereby you fix all this one to be u, so that we have u raised power negative a half equals pi equals to u raised power negative a half. And then that is x squared. It's like we have now u phi equals to u power negative a half. And u is x squared plus y squared plus z squared. So that partial phi partial u partial x will be partial phi partial u, and then times partial u partial x. So when you differentiate this one, we get negative a half u raised power. Now subtracting a half here, then you have minus. So minus a half minus 1. That should give us minus 3/2. So minus a half minus 1 is minus 3/2. So we'll have u, which is x squared plus y squared plus z squared raised to minus 3/2. And then times, differentiating this with respect to x partially, you get 2x. So that will give you a half and 2 cancels out. So we have negative x into x squared plus y squared plus z squared raised power negative 3/2. Similarly, partial phi partial y will actually give us negative a half x squared plus y squared plus z squared raised to minus 3/2. And then I multiply by 2y, which will be negative y into x squared plus y squared plus z squared raised to negative 3/2. And also, partial phi partial z will give me negative a half x squared plus y squared plus z squared minus 3/2 times 2z, a half and 2 cancel, so I have negative z into x squared plus y squared plus z squared raised to minus 3/2. So those are the first partial derivatives. Now, next one, we go to second partial derivatives. So partial squared phi partial x squared will give me the same as partial x, and then partial phi partial x. So we need to differentiate this function with respect to x, this function here. We have this point. Now, you see this is x, and this also have x. So we use product rule. This is u, and all this bracket with this power, call it b. So by product rule, we have u prime v plus v prime u. So u prime is -1. So we'll have just negative x squared plus y squared plus z squared raised to negative 3/2. Plus, now v prime, to differentiate this part, we use chain rule, whereby we fix this bracket. And so we drop, we have minus 3/2 into the same bracket. And then subtract 1 from minus 3/2, which is minus 5/2. And then differentiate again what is inside with respect to x. And we get 2x. And then this answer we have here, then we multiply by negative x, which was our u function. So that this and this cancels out. So this negative and this negative gives us positive. So we'll be adding x by x is x squared into x squared plus y squared plus z squared raised to power minus 5 over 2. Now, a number raised to power minus 5 over 2 and another number raised to power minus 3 over 2. So let me just write. So the first one will be negative x squared plus y squared plus z squared raised to power minus 3 over 2 plus the other one is x squared into x squared plus y squared plus z squared raised to power minus 5 over 2. But then we can simplify this one further by putting this one outside the bracket. So I have x squared plus y squared plus z squared raised to power minus 5 over 2 into brackets. Now, this and this are the same. Or maybe I can start with this part, which is x squared. And here, I have a negative sign. So if I have a number u raised to power negative 5 over 2, another number u raised to power minus 3 over 2. So that I have, if I factor out u raised to power minus 5 over 2, then I need to have u raised to power 1, so that when I multiply u raised to power minus 5 over 2 times u power 1, I have u power minus 5 over 2, loss of indices, plus 1. Minus 5 over 2 plus 1 gives you minus 3 over 2. So therefore, once I've factored out this bracket raised to power minus 5 over 2, because this is minus 3 over 2, then I need just to have power 1 of the same bracket, so that by after simplifying, I still get back my minus 3 over 2 as the power. So I have x squared plus y squared plus z squared raised to power 1. And then when you simplify this, we'll get this equals to x squared plus y squared plus z squared raised to power minus 5 over 2 into x squared minus x squared, and then now minus y squared, and then minus z squared. Power 1 get the same as the same bracket. This is what we have. So this will give us x squared and x squared cancelled, so that we have so remember at this point here, we had 2 dropped minus 2, and then this for just fine. That's okay. So that we have minus there's some 2. So half, and then that's from here. So there's, in this simplification here at this point, after dropping minus 3 over 2, and then x squared plus y squared, so this minus 3 at this point here. So this by this one, so it'll give us 3x squared, not just 3x. So here we need to have this 3 here. So we need to have a 3 here. So that we are not canceling that. So we'll have, so 3x squared minus x squared, and then minus y squared given by that. So we'll have x squared plus y squared plus z squared power minus 5 over 2 into, so this will give us 2x squared minus y squared minus z squared. And then for y, similarly, partial squared phi partial y squared will be partial y into partial phi partial y. So let's go to the first partial derivative of y. So this is the first partial derivative of y. So call this one u, call this v. So by product rule, we have u prime v plus v prime u. So when you differentiate this partial with respect to y, you get minus 1. So we'll have minus x squared plus y squared plus z squared raised to minus 3/2. And then this other part, to simplify this other part here, derivative of v. So you'll use chain rule. The first thing, you fix this part. So you'll drop this power. So plus minus 3/2, and then into x squared plus y squared plus z squared. And then you subtract 1 from this power, you get minus 5/2 times. Now inside this, you differentiate with respect to y. So you'll get 2y. And then you multiply by u, which is minus y. So this minus sign and this minus sign cancels. These two and these two cancels. So that this part will be now y times y is 3. And then by 2, you get 3y squared. So that will have negative into x squared plus y squared plus z squared raised power minus 3/2. Now plus y times y is y squared times 3, we have 3y squared into x squared plus y squared plus z squared raised power minus 5/2. So then we write this as minus x squared plus y squared plus z squared raised power minus 3/2 plus now 3y squared into x squared plus y squared plus z squared raised power minus 5/2. Similarly, you factor out this bracket raised power minus 5/2. So we'll have x squared plus y squared plus z squared raised power minus 5/2 into, so this part will give us now 3y squared minus sign is here. But then I remember this is like, if you have a number raised power minus 5/2, another number raised power minus 3/2. So if I'm putting brackets, then for me to get back my minus 3/2, if this power is minus 5/2, I have to ensure that this is 1. So that minus 5/2 plus 1 is minus 3/2. So the power of this one will be 1, x squared plus y squared plus z squared raised power 1. So that this reduces to x squared plus y squared plus z squared raised power minus 5/2 into, here we'll have 3y squared minus x squared minus y squared minus z squared. When you simplify, you get x squared plus y squared plus z squared raised power minus 5/2 into, so 3y squared minus this would be 2y squared minus x squared minus z squared. So similarly, if you do what we have done for x and y, you should get partial squared phi partial z squared will be given by x squared plus y squared plus z squared minus 5 over 2 into, now we'll have 2z squared minus x squared minus y squared. Just follow the same step. You should arrive at this. So if I had called this one first equation, so if I call this one equation 1, and then I call this one second partial for y equation 2, I call this one equation 3, then it means that 1 plus 2 plus 3, all of them have a factor, x squared plus y squared plus z squared raised to minus 5 over 2. So man, then remember, this is what we have as the partial squared of 5, partial x squared, partial squared of 5, partial y squared, partial squared of 5, partial z squared equals to, so I factor out this factor, x squared plus y squared plus z squared raised to minus 5 over 2 into the first one for x in equation 1, we have 2x squared, and then the others are subtracted. So we have 2x squared minus y squared minus z squared. Next one, I have 2y squared minus x squared minus z squared. And then the next one, I have 2z squared minus x squared minus y squared. And even use brackets. So this is what we have. So now let's evaluate, simplify this. So this will be equals to x squared plus y squared plus z squared raised to minus 5 over 2 into, so I collect all x's together. So I'll have 2x squared. Here I have minus x squared. Here I have minus x squared. Then here I have minus y squared. Here I have plus 2y squared. Here I have minus y squared. And then I have minus z squared. And then here I have minus z squared. And then I have plus 2z squared. Clearly, you see that we'll have x squared, y squared, plus z squared raised to minus 5 over 2 into, so I have 2x squared minus 2x squared, and then minus y squared plus 2y squared is y squared, and then minus y squared, minus z squared plus 2z squared, the same as plus 2z squared minus 2z squared. And clearly, this will give us 0, this will give us 0, and this will give us 0. So we have this factor, x squared plus y squared plus z squared raised to minus 5 over 2, and then just being multiplied by 0, which is 0, and that is the end of the proof. So thank you.